Hey everybody! I believe I just spent a good hour plus recording some videos about this PiDP-8 replica that I put together, and I had the microphone off the whole time. So we're going to do this again. I do want to keep this interesting. I hope that people will find it interesting. I think this is really cool. And basically the one I'm going to redo here and actually post will be just a quick tour of the thing and a little introduction to PDP assembly language, or PiDP-8 assembly language, and you know, maybe you can learn a few instructions or two. I apologize for drinking my tea while I'm doing this, but I have to multitask at this point. It's getting late. So let's go quick tour of the front panel here. As you can see, there are lights and switches. Computers of old were awesome. They had lights and switches. People, you know, how could you trust that the machine is working if you can't see its internal state? And so to that end over here, you can see which class of address is executing, what phase it's in, whether the machine's running or stopped. You've got the accumulator. Of course, you want to know what's in your accumulator at all times. You get the program counter so you can know where it's executing, and you can see memory address and contents and other stuff, which I'm not going to get into now, most of all because I don't know what it is yet. I haven't learned everything about this machine. And then down here you have all of your exciting toggle switches. So on the left side is where you actually enter the data, and then on the right side are some of the controls for it. You might notice that these are grouped in groups of 3, and that is because they represent octal. So when I talk about addresses and things, when I talk about numbers, all of the numbers I'm talking about, I will be using octal notation. 3 bits, you can enter any number up from 0 to 7. And you don't have that annoying hexadecimal to have to worry about what do you do with the letters and things. So stick to 3 bits. Now, the left 2 we're going to ignore completely. Those correspond to the data field and instruction field. We're not going to use those. They're confusing. They just make things difficult. It's a kind of bank switching scheme to access more than 4K words of memory. 4K words of memory, this is a 12-bit machine, so there are 4,096 12-bit words, and that is why there are, in fact, 12 bits here, 4 groups of 3. So we're going to concern ourselves with this 4 groups of 3 here. And so the first thing I will do over here on the on the controls is I will press the stop key. When I press that, it stops the computer. You can see the lights stop blinking. It freezes where it was. I can then press continue to resume execution. Stop, continue, stop, continue. Isn't that great? So let's stop the machine. And now I will let's go ahead and show you how to enter a program. So as I said, there are 4,096 memory addresses to simplify things a bit that we could use. So we can put our program pretty much anywhere we want in memory. I'm going to choose to put the program at location 10 octal, which of course in decimal would be 8, and in binary would be 1000. Okay, so the first thing we do is we put the address that we want to start entering instructions at on these toggle switches. So up is 0, down is 1. So we want to enter address 10 octal. And so essentially of these 4 groups, 0, 0, 1, 0. Okay, 1. So I'm just going a little bit slowly here because I will be using octal addressing a lot, and so it's the kind of thing to get used to. When I say 10, I mean 1 in this group and 0 here. Also, you'll note that these are divided into groups of 3 by these white lines, so it's all nicely lined up for the octal use. So 10, press load address. Load address transfers the state of these toggle switches up to this line here that has the program counter in it. So now this says 10. If I put anything else in here and I press load address, it basically transfers those switches up to there. So that loads the program counter with 10. Now we're ready to enter our first instruction at address 10. What instruction shall we put there? Well, I figure for a tutorial like this, let's go with the simplest possible instruction, which I will call halt. I will call it halt because it is called halt. So what is the opcode for halt? The opcode for halt is 7402. So we're going to enter that here. 7, you do that nicely with your thumb, 4, 0, 2. 7402. And now we press deposit. And deposit will take whatever is toggled in on these switches and store it at the address that the program counter is set to here. So we're going to put a 7402 at location 10 by pressing deposit. Now you'll see what happens there are a couple of things. First of all, it shows the 7402 that we entered. It shows us the address we entered it at, which is 10, and the program counter increments by 1 so that we're ready to toggle in the next instruction and deposit that as well. Of course, this program is a one instruction program because halt stops the computer. So what we can do now if we want to run our program is go 10, load address, so that resets the program counter to 10, and then just press start. And there we go. The program ran and it halted because that's what it does. So load address, start. As you can see, the program counter ticked over to show us what the next instruction would be if it were to execute, but it didn't execute. And also the operation light came on here because the opcodes that start with 7 are in the operation category. So that told us it executed a 7 something instruction. And then it's not running because the halt instruction stops it running. So halt. So that's our simplest possible program. Now let's do something more interesting. How about we increment the accumulator? So we'll make a 2 instruction program. Increment the accumulator maybe even 5 times and then halt. We'll make a 6 instruction program. So 10 is the address we want to enter this at again, same as before. So we're going to reset the program counter to 10, load address, and now we're going to start entering our instructions. What is the increment accumulator opcode? It is 7001. 7001, deposit. And as I said, let's just do 5 of those. So as you see, the program counter ticks over, so we can do 2, 3, 4, 5. We've entered 5 increment accumulator instructions in a row. And now let's go to 7402, which is our halt instruction, and deposit that. Now I'm going to show you a new trick, which is examining memory on a PiDP-8. So we can go 10, load address, and now we want to see what is at address 10. So you press examine. And what examine will do is it shows you in memory buffer 7001, which is what's stored at that address. And it increments the program counter so you can see, you just press examine again and you can see the next one. It's the same, it's the same, it's the same, it's the same. And then finally our halt 7402. Okay, so let's go back to load address 10, which allows us to start the program. I will press start. What do you expect to happen? Have you thought about it? Did you say that you're going to see a 5 in the accumulator? Okay, let's press start. Okay, look at that. You were right. 5 in the accumulator, and then the program stopped because it started at the beginning, accumulator was 0, increment, 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 halt. And so we end up seeing 5. Now, at this point, we can do more interesting things. We can go back to the beginning, load address 10. We can toggle the single instruction toggle, which means now when I press start, it's just going to execute 1 instruction and then it will halt. And then every time I press continue, it will execute the next instruction. Now there's one thing that always confuses me here, which is that I don't know if this is a real PiDP-8 thing or just a simulator thing, but it shows the program counter being ahead of where it should be in my mind, right? So we executed the code at 10. I would expect the program counter to be showing 11, but it in fact shows 12. But memory address shows 11. So I think what happens here is it's actually halting after it has fetched the next instruction. And it's already sort of preloaded program counter with where it will be after the next instruction, even though the next instruction hasn't even executed yet. So it's kind of like 1 step ahead if you look at the program counter. So really what you kind of want to look at is memory address in this case. In any event, we've only executed 1 instruction, the instruction at 10, which was a 7001 increment accumulator, and that's why the accumulator has a 1 in it. If I press continue, the accumulator now has a 2 because we executed the next one. and then a 3, and then a 4, and then a 5, and then finally a halt. So when I press continue, it's no longer continuing because the program has halted. Cool, right? Okay. Now you say, that's all well and good, but I'd like to see some loops. So let's do some loop-de-loops. How about we go back to the beginning again, load address 10, and this time we will do a very simple 2-instruction program. Increment accumulator, jump to the beginning. Now, have you memorized increment accumulator yet? 7001, deposit. And now what does a jump instruction look like? A jump instruction starts with a 5. 5, and then the address you want to jump to, more or less. Cheating a little bit. But 5010, right? Because we want to jump to 10, which is the beginning of our program. So 5010. Deposit. Okay. And I just noticed this. I didn't even see this before. It helpfully lights up the instruction that you just entered. So cool. All right, so now we can, once again, let's try that examine again. So we load address 10, we can examine it, and we see 7001 followed by 5010. So that's going to increment accumulator and jump to the beginning. Load address, start. What do we expect to happen? Yes. So of course the accumulator is incrementing, but it's incrementing very, very, very quickly, faster than the eye can see, faster than the camera can see. So if we press stop here, it'll be at some random value, continue, stop, single step, how about that? Continue, continue, continue. So what we're seeing here is we increment the accumulator, then we jump back to the beginning. Increment, jump, increment, jump, increment, jump, increment, jump. And as you can see, we show the instruction that was executed, and we show the program counter updating to show the next instruction that would run. Okay, cool. So this is going too fast. What if we wanted to slow it down a little bit and make it count in a more visible way? How could we do that? Well, let's think about the way that this program works. It has it's essentially 2 instructions: increment, jump, increment, jump, increment, jump. What if we spread those out a little bit, and in the middle we put a delay loop? Okay, so we're going to keep our increment at the beginning, and at the end we're going to jump back to the beginning. But in the middle we're going to loop around for a little bit and delay. So that we need to learn one more instruction, which is the ISZ, increment and skip if 0. The way this one works is it increments a memory location in the machine, and if that memory location is 0 after the increment, then it will skip the next instruction. Otherwise, it will execute the next instruction. So if we do an increment and skip if 0, followed by a loop back to that increment and skip if 0, it will continue doing that until that memory location basically wraps around. So it'll do it 4,096 times, and when it wraps around to 0, then it will skip the jump, and it will move on to the next instruction, which will then be a jump back to the beginning, which increments the accumulator and continues. Makes sense? I hope so. If not, I'll explain it again after we enter the code. So let's do our usual thing. We're going to put 10 in here, load address. And we're going to start entering instructions. What's the first instruction? Increment accumulator, 7001, deposit. Okay, now our new instruction, increment and skip if 0. This opcode starts with a 2. 2, and then the address of the memory that we want to increment. In this case, it's fairly arbitrary. You could stick any piece of memory somewhere in the machine. For some reason, most of the demo programs that I've seen when people get to this point, they seem to use address 34. Perhaps because everybody copies off each other, I don't know, but we'll do the same thing. So 2034. Okay, so this is increment address 34, and if it increments to 0, then skip the following instruction, deposit. Now, what is the following instruction? Our old friend jump, which we just learned a minute ago, which is 5. And what are we going to jump to? We're going to jump to the increment and skip if 0 that we just entered, which happened to be at address 11. Okay? Deposit. And now that's the inner loop. So increment of skip of 0, and then jump back. And now if we skip over that jump, we get to the following jump, which will jump back to the very beginning. So instead of jumping to 1, 1, it's going to be the same jump to 1, 0. Deposit. Okay? Makes sense? Hopefully we've said it enough now. So now if we examine this again, 4 instructions in this program from the beginning. 7001, which is increment accumulator. 2034, which increments the memory at 3, 4, and then skips the following instruction if it's 0. The following instruction is 5011, which jumps right back to where we were. And if we skip over that, we get to 5010, which jumps back to the very beginning. And so the practical upshot of all of this, load address, start, you know what it's going to do? It's going to do that. So the accumulator is incrementing, but at a considerably slower rate, so we can actually see the bits moving across there. And again, we can stop this single step if we like. And so if I press continue here, you'll see that we are moving between 2 instructions, one of which is incrementing. This is nice because the memory buffer here shows you what is at that location 3, 4. So that's the thing we're incrementing. And we keep jumping back, ISZ, jump, ISZ, jump, ISZ, jump. And this would continue all the way until all of these LEDs are lit. And then when this wraps around and hits 0, then we would continue. You get the idea. So there is our quick tour of the PiDP-8 replica. And there's you learned a bunch of instructions. So I think it's pretty cool. See ya.